So, welcome to the 8th lecture in this series. Right. So, in the last class what we were discussing about some properties of fluorescence, right. So, I discussed about Kasha's rule. Here we said that the wherever you are going to excite the molecule, the emission will come from the lowest vibrational level of the first singlet excited state. That means, the second one will come automatically, that emission will not going to depends on the excitation wavelength, right. So, the second one is that no excitation wavelength dependence of fluorescence spectra. The third one what we have seen is that emission will always be at the longer wavelength than the excitation, right, or absorption. So, emission is at longer wavelength than absorption. Here obviously I am referring to the maxima, right. The point number 4, the property number 4 is that excitation spectra is same as the absorption spectra, right. So, excitation spectrum is same as the absorption spectrum, right. And the property number 5 is the absorption or excitation spectra has a mirror image relationship with the emission spectra, or I can write the emission spectra is mirror image of the absorption or excitation, because they are same, right. Spectrum, right. Okay. So, and this emission is at longer wavelength than the absorption. This is nothing but my Stokes shift. So, here is my Stokes shift, right. So, these are the 5 properties of the fluorescence, and now today what I am going to discuss is 4 different parameters of fluorescence, right. So, fluorescence parameters. So, the number 1 is being to be the fluorescence intensity, right. So, here is my fluorescence intensity. Generally denoted by either I or F, right, whatever you want you can use it. So, either I or F, general notation of this. Before continuing this, let me tell you clearly that these set of properties of the fluorescence are general property, and there are several exceptions on this. Some molecules they do not emit from the lowest vibrational level of the first singlet excited state, instead it is emitting from the second electronic state and so on and so forth. So, there are some many exceptions, but these are the general rules, right, what I said, that 5 different properties of the fluorescence. Okay. So, the first parameter is fluorescence intensity, as I said, and is denoted by I or F, right. So, this fluorescence intensity is nothing but the intensity in the fluorescence spectra or emission spectra that I have showed you. So, here is my intensity versus wavelength plot, intensity versus wavelength plot, and this is the emission spectra, let us say, for a particular molecule in a particular solvent. So, you can refer either to the intensity of the maxima, right. So, I can write intensity at lambda max, I can write it like this way, or I can integrate the whole part and I can say that the intensity of the area. So, I can also say like that. So, the area is also intensity, right. So, this is the area. So, this is one of the property. Some molecule shows a strong intense emission, some molecule shows a weak emissions, so on and so forth. However, you automatically you can understand that if the number of molecule increase, the fluorescence intensity increase. So, this fluorescence intensity is a function of the concentration, right. So, this is a function of concentration. If the excitation light you use to excite, right, the sample is very high, that means the photon flux is very high. So, depending on the absorption cross section, more molecule are going to absorb this light, right, photons. So, more molecule will go into the excited state. So, in that case, more fluorescence will come from the sample. That means, this fluorescence intensity is also a function of excitation light intensity. Right, excitation light intensity, and obviously this is also depends on the molecule to molecule. So, the molecular property is also involved in this fluorescence intensity. So, also involved the molecular property. So, you see 1, 2, 3, that means this fluorescence intensity is not a very useful parameter to deal with, because it varies with concentration, it varies with excitation light intensity, and obviously it is the property of the molecule itself. And so better, so people generally do not use this fluorescence intensity to characterize the fluorescence property of a molecule. Instead, people use this fluorescence quantum yield. Generally denoted by this symbol PhiF, right. So, this fluorescence quantum yield is defined as rate of decomposition of the excited state, right, by emission of radiation, right, by emission of radiation divided by rate of absorption or rate of creation of the excited state, right. So, this PhiF is defined by rate of decomposition of the excited state which involve emission of photon, right, which involves emission of photon divided by rate of creation of the excited state, right, rate of creation of excited state, which is nothing but the rate of absorption, right. So, this is rate of absorption. So, phi f is defined like this. Let me explain it by taking a simplified Jablonski diagram. So, in the last class I showed you the Jablonski diagram. So, now let me show a much more simplified version of this Jablonski diagram, right. So, I have this ground electronic state over here, this is my S0 state and this is my first electronic excited state. Let us say this is my S1. I have some sort of vibrational structures over here, right. Now, I excite this system from here to here, then the system will relax back to the ground state. So, this is my absorption of radiation, and eventually the system will come back from the higher vibrational level of the first singlet excited state to the lowest vibrational level of the first singlet excited state. Those are the vibrational relaxation. I can give some rate constant to it. Let us say I am giving this as k VR, right, rate constant of vibrational relaxation, right. Then the system will come from this state to the ground state by emission of radiation, right, emission of photon. That means, this corresponds to the kr, or there may be some other pathway that the system will come from the excited state to the ground state without emission of radiation, that is the non-radiative pathway, right. So, I will have the other channel like this way, which is k nr, right. So, after excitation I am now going to have these three different rate constants over here, kVr, kr and knr, right. Now, only this decomposition channel of the excited state, this decomposition channel of the excited state involved the emission of radiation, only this one, right. Other two are not. So, this one is and this one they are not, right, only this one is the deactivation channel which involves the emission of radiation, right. So, now if I want to write this phi f, so this phi f is what? The rate of decomposition of the excited state which involves emission of photon, right. So, this will simply be kr, right. So, I simply write here kr divided by the rate of creation of the excited state, that is rate of absorption. That means, this one plus this one plus this one, right. This is my total rate, right, of the absorption. So, I just write kr plus k nr plus k Vr. So, this is the fluorescence quantum yield of this particular compound. Now, if you increase the concentration, what will happen? Again, this Kr plus Knr plus Kvr, they will not change because they are rate constant, right. So, it will not going to depends on the concentration of the molecule. So, it is also independent of the concentration of your system, right. So, this phi f or fluorescence quantum yield is independent on the concentration of your sample, it is independent on the excitation light intensity, but and it only reflect the property of the molecule, right. So, over the fluorescence intensity, fluorescence quantum yield is a better parameter to define the fluorescence, right. Okay. So, I am going to show you later that how we are going to measure or estimate the fluorescence quantum yield for a particular compound. Now, let us move to the property parameter number 3, which is fluorescence lifetime. generally denoted by the symbol tau, right. They are denoted by the symbol tau f. So, if you ask what is the definition of fluorescence lifetime, is the average time the molecule spend in the excited state is the fluorescence lifetime, right. Let me explain this by taking again this simplified Jablonski diagram over here. So, let us say this is my ground electronic level, this is my excited electronic level, and by absorption of light you have created the population over here, right. This is the lowest vibration level, you have created the population over here, right, and that population has been created instantaneously because absorption is just a very fast process, like less than a femtosecond process, right. So, instantaneously you created a population at this excited state, right. So, and let us say the concentration of this excited state population is n star, right. So, and obviously this excited state will not going to stay there forever. So, it will come back to the ground state, and I talked about the two different type of deactivation, one is radiative, another is non-radiative, and let us write this as the radiative one is like Kr as usual, and then non-radiative one as K N R, right, Kr and K N R. Okay, so, let us write it properly, right. The rate of rate constant, and K N R is non radiative decay. This is fluorescence, right, we know this is my fluorescence, right. So, but remember that both of these process depopulate the excited state, right, both of these process. So, if I now write how the excited state population is changing with time, that means minus d n star dt, right, that is how the excited state population is changing with time. So, minus d n star dt, that will be equal to K r into n star, K n r into n star, right. So, this is equal to K r n star plus K n r n star, right. So, what I have is equal to minus d n star dt equal to n star K r plus K n r, or you can write minus d n star by n star equal to K r plus K n r dt. Let us integrate it, right, integrate it. After integration and putting the boundary condition of at t equal to 0, the excited state population is maxima, right. So, n star is equal to n star 0. So, immediately what we are going to get is n star at time t equal to n star 0 into e to the power minus t by tau f, where tau f is equal to 1 over K r plus K n r, right. So, here you see this is this equation, right, this equation define how the excited state population deactivated, right, deactivated, in which time scale it is deactivated. So, suppose you have started with 100 molecules in the excited state. This equation tells me or suggesting me that it is not the case that these 100 molecule will come back from the ground excited state to the ground state after a certain time in a suddenly, right. It is not like that, because if I plot this, right, I can plot it n star versus T, right. Let us plot it. N star versus T. So, at time t equal to 0 over here, here is my 0 time, right. At time t equal to 0, right, this n star t equal to n star 0. So, it will start with n star 0 value, right. So, this is my n star 0. When t is very high, right, infinity, then this is e to the power minus very high value. So, that means this n star will be 0. So, let us say for very high value of t over here, this value is almost 0. So, I start from here, I will end over here, right. In between, let us say when in between it follow this exponential behavior, right. So, the function will looks like this. The function will looks like this. It means that initially at time t equal to 0, there is this much of population. As time goes, the population is decreasing here at this time. At this time, the population is now this much. At this time, population is now this much, right, and so on and so forth, right. When this t is equal to tau f, right, when this t equal to tau f, what will get? So, when t is equal to tau f, because this tau f is the time constant, inverse of the rate constant, you see this tau f is the time constant, that is inverse of this rate constant. So, I just wanted to see that when t equal to tau f, what will happen, right. So, when t equal to tau f, what I am going to have over here? N star t is equal to n star 0 e to the power minus 1, right. So, this is 1 over e, right, is 1 over e. That means, the population, right, will decay about 37%, right. So, 37% is remaining, right. So, population has been decayed about 63%. So, this n star is 63% of the original population decreased. Isn't it? So, at time t equal to tau, let us say over here, somewhere over here, this is my tau f. So, here 63% population has been decreased, 63% population has been decreased. Okay. So, so I should write decreased, otherwise, yeah. So, decreased. That means, when t equal to tau f, right, some fraction of the population is coming back from the excited state to the ground state, and majority is coming before t equal to tau f. This is before t equal to tau f, and this part is after t equal to tau f, or when t is greater than tau f, and where here is t is less than tau f, isn't it? So, the population is coming from the excited state to the ground state, not of a sudden, not of a sudden. So, this is important. So, continuously the population is coming from the excited state to the ground state, right. So, and the average time the molecule spend in the excited state is denoted by this tau f, the fluorescence lifetime, right. As you can see that here it is the inverse of this rate constant of the deactivation, it does not depend on the concentration itself, right. So, the this is independent on concentration, it is also independent on the excitation wavelength, because in case you will use the strong excitation power, you will going to send more molecule in the excited state. So, it does not depend on the concentration. So, it will not going to depend on the excitation light intensity. So, this fluorescence lifetime is also a very important parameter of fluorescence, which does not depend on the concentration or the excitation light intensity. Okay, the fourth parameter is very simple one. So, let me quickly discuss this before we finish this today's lecture. So, this fourth parameter is the emission maxima, right. So, the molecules, right, every molecule has this characteristic emission maxima. Some molecule emission maxima is in the orange color, some molecule emission maxima is the blue, some are green, and so on and so forth, right. So, by knowing the emission maxima, right, we can also comment on this molecular property, and that is why the emission maxima is one of the important parameter of the fluorescence. So, before I end this here, so let me tell you that this fluorescence quantum yield, right, I missed it while I discussing this fluorescence quantum yield. The value of this fluorescence quantum yield could be anything between 0 and 1, right, could be anything between 0 and 1. When this Kr plus Knr value is much smaller than this Kr, right, then this is nothing but Kr by Kr. So, this is equal to 1. When these values are much more compared to Kr, then small quantity divided by very large quantity, that means the value is close to 0, right. So, depending on the molecule, depending on what? Depending on the photophysics of the molecule, right, which I will probably discuss later. That means, how much is the radiative rate constant, how much is the non-radiative rate constant, right. So, the fluorescence quantum yield varies a lot. So, for example, rhodamine 6G in ethanol, the fluorescence quantum yield is 0.94, very high, right. So, it tells me that the non-radiative rate constant for this molecule is very low, right, but radiative rate constant is very high. For example, coumarin 153 in ethanol, this value is about 0.54, right. So, is 50-50 kind of thing. Whereas, for the ANS 1,8-anilinonaphthalene sulfonate, in short ANS, in water, this value is about 0.003, right, 0.003. So, it means the radiative rate constant is very high. So, most of the energy from the excited state is dissipating in terms of heat, not in terms of light, right. So, that is why the fluorescence quantum yield is very low in this case. Okay, so, we will finish here and we will see you in the next day. Thank you very much.